Vision isn't the only sense in the animal kingdom that's evolved in rather curious and amazing ways. Let's take taste, for example. Did you know that pigs and rabbits have almost twice as many taste buds on their tongue as humans? While we taste with our tongue, taste receptors in other species can be actually located elsewhere to detect the presence of certain chemicals. Butterflies, for example, have taste receptors on their feet. So do honeybees. They have taste receptors on their jaws, forelimbs, and antennae. It may sound strange, but this makes a lot of sense if your job is to find sweet nectar for the rest of your hive. You want to be able to taste your environment at as many points as possible. But the ultimate prize for tasting perhaps goes to the earthworm, whose entire body is covered with taste receptors. Imagine if you could taste with any part of your body. Another amazing sensory adaptation in the animal kingdom occurs in mechanosensation. Recall that mechanosensors in humans provide physiological foundation for the senses of touch, hearing, balance, and pain. Other species can also use mechanosensation to detect other changes in their environment. Ants, for example, can detect small movements through up to 5 centimeters, or roughly 2 inches, in densely packed earth. Compared to the tiny size of their body, that's quite a distance. Or take crabs, which use mechanosensitive hair cells on their claws and other parts of their body to detect water currents and vibrations. Similarly, grasshoppers and butterflies have hair cells all over their bodies and wings, respectively, to detect changes in air movements and pressure. You might have also heard that a large variety of animals possess a sense to detect magnetic fields. Certain migratory birds, for example, are believed to use magnetic cues in addition to several other factors to find their way across the globe during migration season. Similarly, earthbound salamanders and frogs are thought to use magnetic field orientation when they have to find the nearest shore, such as when they're escaping from a predator. Animal behaviorists have studied these natural movement patterns for about half a century, and while the existence of magnetosensation is no longer disputed, it's not yet known by which biophysical mechanism and by which receptors magnetosensation is actually achieved. Another sense that is more highly developed in the animal kingdom than in humans is thermoception. While humans can feel the warmth of an object upon direct touch, and depending on the heat source up to several feet or meters away, bats, for instance, can detect the warmth of an animal from about half a foot away using their nose leaf. With this same sensory organ, bats can also find food, most often insects, up to 5 to 6 meters away. And they can even get some information about the type of insect using their sense of echolocation. The prize for thermoception goes to snakes, however. Pit vipers, for instance, have a heat-sensitive organ between their eyes and nostrils, which allows them to respond to temperature changes as small as 0.002 degrees Celsius. That's 1/500th of a degree, impossible for humans to perceive. This is especially useful for hunting, and it allows these predators to find their prey, even if it's hiding out of sight. One final sense unique to the animal kingdom is electroception, or the ability to perceive natural electrical stimuli. Having been observed almost exclusively in amphibious or aquatic animals, electroception is used for both detecting objects and for communication. Since water is a much better conductor of electricity than air, this is perhaps not too surprising. Humans have been familiar with animal electricity since ancient Egypt. Electric catfish found in the Nile River are featured prominently in Egyptian murals. Similarly, the ancient Greek philosophers were all familiar with the stunning charge of Mediterranean rays. So even though the modern theory of electricity wasn't established until the 18th century, our ancestors knew there was something special about certain kinds of fish. Eventually, after the advent of modern tools that can measure electrical currents, researchers began to suspect that such animals might not only be able to generate electricity, but might also be able to detect its presence in the environment. Today, we know that electroception is used in a number of ways in the animal kingdom, both passively and actively. Species that are able to detect electricity in their environment without producing it themselves, such as certain sharks, catfish, and the duck-billed mammalian platypus, are known as passive electroreceptors. They can use electricity to detect their prey, even if they can't see it. Because electrical signals perceived by these animals are often small and far away, passive electroreceptors must be very sensitive. In fact, most passive electroreceptors can detect thresholds on the order of nanovolts per cubic centimeter. This ability makes them effective hunters, because prey create electric fields when they move their muscles and when their hearts beat. Additionally, some species actively generate electricity, including various species of electric fish, like the electric eel. And they can detect objects in their environment by perceiving how the electric field they produce around themselves is modified by the presence of other objects. This reception takes place in electroreceptive sensory cells embedded in the fish's skin, originally described as the electroreceptive retina. In addition to electrolocation, many fish also use their active electroreceptive sense to communicate as part of their social behavior. For example, each species of fish has their own characteristic discharge profile from the electric organ. In some species, this discharge profile is highly sex-specific, so that this fish can use their electric sense to detect their sexual counterparts. This electrical discharge can even be modulated during mating behavior in some species. An electric courtship song, if you will, much like the ones vocal songbirds use above the waterline, but obviously less complex. Does a sixth sense of electroreception exist in humans? To date, there's not much credible evidence to support it, and physics speaks against it. All known electroreceptive species are aquatic, which, as mentioned earlier, makes a lot of sense since water is a much better conductor than air. Hopefully, we've given you a sense of how amazing and diverse sensory systems can be. A lot goes into how we perceive the world, and there's much left to be discovered and understood.